Hey, Miss Tate.
Hey, Momo, how are you?
Good. How are you?
I'm good. I'm good. Can you see the screen up here?
Move it up a little bit. All right. Yeah.
Are those clear?
Yep.
Okay. All right. Milani, you can go live with me on Monday. Okay. So how you been?
Good. How about you?
I'm great. Trying to hang in there. Trying to hang in there.
Yeah. I feel you.
Yeah. We're gonna wait for about another minute so people can join in. I see we have 7 people on with us.
Yeah.
Okay. As we are waiting, you all can start typing in your answers to our warm up that's there. Hello, Stuart. Hey, Taymani. Hey, Jewel. Okay. All right, everybody. So we have a few people on. Let's get started with our warm up. Momo, please read. Can you read our warm up, Momo?
Huh?
Can you read our warm up, please?
Yep.
Okay.
Which type of heat transfer cooks food in a microwave? Explain.
Okay. So at this point, I want you all to type in your answer in the comment section. Type in your answer in the comment section. Do that now. All right. Hey, Kelly. Radiation, radiation, radiation. Very good, very good, very good. It is radiation. Why is it radiation? Can someone please explain to me? Momo, can you explain to us why it's radiation?
Because a microwave has like heat waves.
Okay. And what does that mean?
So like I don't know how to explain it. It's like since the microwave kind of have heat waves, it's going towards the object and like heating it up a little bit.
Is it actually touching the object? What's actually going to the object in order
Heat.
for you say heat?
Yeah.
But how? So is it touching it directly?
Yeah.
You sure the heat is touching
No.
it
Hold
directly?
up. No. 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 No.
Or is it going through, what is this?
Wave.
It's going through electromagnetic waves, okay? And we're going to get some more detail about that today, okay?
Yeah.
So Ms. York Tyson said, couldn't you argue that it is convection too? Yes, you could. Um, it says heat from the microwave is warming up the food. Yes, you can, because typically when you're heating up your food in the microwave, and let me turn it around so y'all can see me. Typically, typically when you're warming up your food in the microwave, um, the first initial thought is radiation because of the waves that's inside of it. However, we can argue, just depends on the type of microwave that you have, because it could be a convection system where the hot air heats up the food and it goes up to the top, and then the cold air goes around. So it's sort of cyclical. So that's why sometimes if you are heating up your food and it's still cold, what should we do? if you're heating up your food in the microwave and it's still cold, what do people typically do to spread that heat around? Momo, what you think?
Add more time.
You can add more time, but what do people typically do to speed up the process if they realize that some part of it is hot and other portions are not? Hey, Grace.
Kind of spread it around and mix it up.
Thank yes. You actually stir it around, okay? Stir it around. Very good. All right, so by the end of the lesson, we will be able to evaluate heat transfer via interactive examples to differentiate conduction, convection, and radiation. So, of course, we're going to finish on with our topic from Monday. All right, our agenda, we did our warm up. We sort of reviewed, we want to review heat transfer again through a kitchen activity as well as interactive simulations and a YouTube video to follow up. All right. Momo, can you read the very first one with the hot cocoa? Can you read that?
Mm-hmm.
Go ahead.
If you have a hot drink on the table and wait for a while, does the drink heat up or cool off?
Okay, what happens to it?
It cools off.
Why does it cool off?
Because if you leave it like alone and not heat it up or just not even put it in the fridge, it can cool down by itself like the heat is leaving the object.
Very good. So the heat is leaving the object, meaning the heat will go from the hotter area to the cooler area. And in this case, the air, let's say if that's on your kitchen table, the air on the kitchen table compared to that hot drink is cooler. Correct?
Yep.
All right. So Golden Nugget said, is this in the packet? Mr. Golden Nugget, we will explain it. I've explained that on Monday. So let me go back for you. If you take a look here,
That is in our week 4 packet.
this should be in your week 3 packet.
Oh, week 3 packet.
This should be in your week 3 packet. Okay. If you take a look here, let me make this a little bit. Okay. This should be in your week 3 packet. However, I am not sitting here going over the answers question by question. I am doing an entire lesson, and by the time the lesson is over, you're able to answer these questions. Okay? All right, my loves. Let's get back to what we're doing. Everybody understand that? If you understand what I just said, please give me a thumbs up so I can move on. All right. So, same thing with the ice cold drink on the table. If you leave the cold drink on the table and wait for a while, does a drink heat up or cool off?
Heat up.
Why does it heat up?
Basically, it's the opposite. So when you like have a cold drink and you set it on the table, and like you said, the kitchen table is gonna kind of put that warm in it, and it's just gonna rest and then get warmer as time goes by.
Absolutely. So the hotter air in your kitchen is hotter than your actual iced tea or cold drink. So that heat transfer is gonna go from the hotter object to the
Cooler
object. Very good. All right. All right. So when it comes to heat, basically what it means, heat is actually the movement of thermal energy. Of course, we already said it's going to go from the hotter object to the cooler object. When it comes to temperature, is the average measure of the average speed of particles. Okay. And last but not least, when it comes to thermal energy, this is the total energy of all particles in the object. Thermal energy will determine how hot. Well, the particles in thermal energy will move depending on how hot or how cold that item is. Okay. Taimani said, if you have a cold drink, it stay cold but turn hot. Okay. It's melting the ice, which makes the drink hot. So if you leave the cup out on the table and you're melting the ice, yes, it's going to make the drink It's going to warm the drink up. Okay. Any questions about this? All right, let's move on right here. Can you see these words, Momo?
A little bit.
A little bit. What about now? Is this better?
Yeah. All right.
Okay.
The atoms inside of everything are always jiggling and bouncing around. They have kinetic energy. A
Stop right there. Stop right there. What does kinetic energy mean?
like endless energy, probably.
It's right there. Think about the sentence you just read. It says the atoms inside of everything are always jiggling and bouncing. If you're
Yeah.
jiggling and bouncing, what are you doing? Are you staying
Moving.
still?
No moving.
You're moving. Okay, so the word kinetic means to move. You got that?
Get out the way.
Pretty much. Pretty much. Okay, so a thermometer can measure the kinetic energy and tell us the temperatures of something. The more jiggling, the higher the temperatures. So we take a look over here. Okay, we have the colder water or cold water. It's moving. The particles are moving, but it's not as moving as fast as the hot water. Why is that?
Because the higher the temperature, the more faster they move.
Absolutely. Okay. So think about that. If you were to boil a pot of water on the stove, you're trying to cook your hot dogs or your noodles or what have you. The hotter the temperature, the more they actually move. All right. Let's move
Yep.
on. Take a look here. Can y'all see this?
Yep. Energy flows. Oh,
I'm sorry.
it's okay. Energy flows downhill. When you ski down, not up. Thermal energy does the same thing. It flows down a temperature hill. Flowing flowing thermal energy is called heat. Heat always flows from hot to cold.
Always. It will always flow from hot to cold. All right.
Mm-hmm.
It says hot water have more energy than cold water. Yes, we know that. We know that because we have added heat energy to it. All right.
Mm-hmm.
Take a look at this example here. Can you see?
Mm-hmm.
All right. Right here we have a cold room air. We have
Mm-hmm.
cold room air. We have a hot coffee. Okay. Remember, heat always flows from hot to
Hot to
cold.
cold.
If I was to tell you to draw arrows on this picture as far as where the heat is going to, what would you draw? What arrows, where would they flow?
A down arrow,
Down arrow from where?
like top to bottom.
How so?
Like, I don't know. Huh. So
So remember, if it's flowing from if heat flows from hot to cold, right?
yeah.
We know that this is hot coffee,
Mm-hmm.
okay? And it's sitting on the table. This is a cold room. Where will the heat travel if you let it sit there?
Down.
Down where?
Down to down to the bottom, like to the table.
To the table?
No, like no, like it will travel down like all the way down. Like I don't know.
Okay, let me give you
Yeah.
a better understanding. Look,
Oh, oh
if this
travel up.
if this is hot,
Oh, I'm stupid.
you're not stupid. You're not stupid. If this is hot, it's going to go to the cold room air. Remember, it's going to go from hot to
To
what?
cold.
To cold.
Oh, I'm done.
No, you're not dumb. You're not dumb at all. Okay, everybody got this? It says energy is packed from particles. It will travel upwards, yes, Jewel, or outwards. Okay, it will be like outwards, not just up. Okay, let's go here. It says another example. Can we see this, y'all?
Yeah.
Okay, you're holding an ice cream cone at room temperature. How does heat flow between the ice cream hand and air?
All right, so this is cold to hot.
Think about this. Think about this. So
Mm-hmm.
we know our body temperature is what?
98.6 degrees.
98.6. The room temperature is roughly 77 degrees. And of course, we know ice cream is much colder than this, correct?
Yeah.
All right, ice cream is at 32 degrees Fahrenheit. So this is the room air. This is someone's hand holding the ice cream cone. How does the heat flow between the ice cream cone, the hand, and the air?
It'll go towards each other, probably.
Say it again.
Will it go towards each other, or?
It towards what? So actually, will it be more than one arrow?
Yeah.
In this case, Reek
Like,
said, hold
the
on, wait a
hot
minute.
air goes to the ice cream because hot to cold.
Okay, the hot air goes to the ice cream. Okay, so that's correct. That's one arrow. Very good, Tyreek. Taimani said the energy from cold and hot temperature. What about it, Taimani?
Because you got your hand at the room temperature touching the ice cream. So that's another arrow because it's going the warm air from your hand plus the cold air is making it like go down.
And that will be very correct. Very, very good. Okay, so in this case, we have the
3 arrows.
body heat, of course. We assume that the hand is temperature. We
Yeah.
assume that our hand is somewhat close to our body temperature. So heat is going to flow from the hand to the air, and from the hand to the ice cream, and from air to the ice cream, because we know that the air is hotter than the actual ice cream.
Yeah.
That's why we don't leave, when we come from the grocery store, we don't leave our stuff out on the kitchen counter, or else your feelings will be hurt.
Yep.
Right?
Yep.
Let me get a thumbs up if everybody has that. Tariq said it's still hot to cold. The hot temperature in a room melts the ice. Absolutely. Very good, Taimani. Very, very good. Thank you all for paying attention. Very good. All right. Another example here. Very good. The water is boiling on the stove in a teapot. How does the heat flow in this particular temperature? How does the heat flow in this picture? Can y'all see the picture or no?
Yeah.
So how does it flow in this picture? We have the kettle here, flame, room air.
So it's kind of like the kind of opposite. Stove and stuff will go up to the little teapot, and then you have the surrounding air going down to that teapot as well.
You have the surrounding air going to the teapot?
Like kind of heating up like kind of the top of it. Because if you have the room temperature and then you have the stove, boom, boom, boom.
So let me ask you this. The room temperature, is that going to be cooler or hotter than this?
Cooler.
Cooler. Remember, heat is going to go from
hot to cold.
Right. So the heat from the burner goes to the kettle. Absolutely. The heat energy from the stove hits the kettle to make the water or tea hot. Very good. So you see those 3 arrows?
Yeah.
In order for any of this to be possible, first, this flame has to heat the pan or the tea kettle or the pot. Okay. Then as it's boiling, you see that a lot of it starts to escape into the atmosphere. Okay. When this pan is actually touching this flame, what type of heat transfer is that called? Conduction, convection, or radiation? When this is directly touching the flame.
Conduction.
That is conduction. Very good. Okay. However, once it starts to boil, what type of heat transfer is that?
Convection.
Convection. Okay. And if it's sitting here for some time, you'll start to see the gases escape. And in this case, when it comes to the tea kettle, this is a little old school tea kettle. Once you start to boil and the gases escape, this will make noise, and you'll see not the flames, but the smoke in the air, and that's how it goes to the actual air, or goes throughout the room. Once it goes throughout the room, what type of heat transfer is that? So if this was to boil,
Mhm.
and I was to put my hand like right over here, and it's um, waves of gas coming out this way, what type of heat transfer is that? It's not conduction.
It's radiation.
It's radiation. Okay. Everybody with me? The steam, steam, very good, very good. Okay. Can we move on?
Yep.
All right. So we just talked about the three forms of heat transfer real quick. Did that. If I was to give you all a bowl of soup,
Oh gosh.
how would your hands feel if you had a bowl of hot soup?
They will feel warm, kind of hot,
You would feel warm, kind of hot. Okay. Why?
because the heat from the bowl, from the soup, hits the bowl, and then it hits your hands when you carry it.
And what type of radiation? I'm sorry. What type of heat transfer is that?
Conduction.
Absolutely, because that is direct touch.
Yep.
Okay. On the flip side, oh my goodness, you see this big snowball right here?
Oh, snowball.
You see that huge snowball?
Yeah.
How will your hands feel if you were to touch that snowball?
Cold.
Why?
Because you touching the snow, and the snow, when you touch the snow, the snow kind of melts on your hand, but it's cold. Like,
So why does snow actually melt when you touch it? What is happening to thermal energy?
cause like it's basically convection.
Is what?
It's convection.
You sure? Remember,
Or
if you're touching it, if you're directly touching it,
oh wait, that's conduction.
okay, so what is happening? We know that your hands are cold. Your hands become cold after you touch this snowball, but please tell me why.
Uh, because you touch the snow and it melted on your hand, but it became cold because the snowball's cold, and basically the snow touch your hand. Well, you touch the snow with your hand, and then the snow's cold, so your hand became cold. Our hands are at room temperature.
Oh, okay, so back up, back up. In your hands, do you have thermal energy? Tariq said we are warm. Yes, we are absolutely warm. All right. But
Mm-hmm.
if we touch a snowball, your hands become cold. Why? What has happened to the body? What has happened to your heat in your body? What did you lose?
Heat, warm heat.
Thank you. You lost thermal energy. And when you lost that thermal energy, the energy went towards the snowball. Now,
Yeah,
theoretically, the snowball should start to do what?
melt.
It should start to melt. You see that heat transfer? See how that
Yeah,
happens?
yeah.
Okay. And that's why your hands become cold, because that snowball is taking the heat from your hands.
All right.
Everybody got that?
Mhm.
Give me a thumbs up if you have that and understand. Thumbs up if you understand. Thank you. All right, let's move on. So we already said conduction is direct touch, transfers between solids. Keep in mind, conduction is heat transfer between solids. Okay?
Mhm.
Convection is heat transfer into or out of moving fluids.
Mhm.
All right? So let's take a look at convection occurs when one of the things heat is transferring in or out of a liquid or a gas. A fluid is a liquid or a gas. Okay?
Mhm.
So what is water?
Liquid.
Water is a liquid slash a fluid. Okay?
Splash of fluid.
What about syrup?
Syrup. Fluid.
Fluid. Okay? Um, so when it comes to convection, is heat transfer through moving liquids.
Move. Huh? What'd you say?
I said since it's convection is heat transfer through moving fluids or through moving fluids. I'm sorry. All right. So
Mhm.
let's take a look at the space heater. This space heater has a fan to help improve heat transfer with convection. Remember, the hot air is flowing because of the fan. It will
Yeah.
warm up. It will warm up something faster than if the air was not moving. Okay. So right
Yeah.
here, sorry, over here, this is the actual I'm sorry, heater, space heater. Okay.
Yeah.
Take a look at the second picture.
Mhm.
This person, it says, this is how me. Have you all heard about the wind chill factor? You know what the wind chill factor is?
No.
All right, this is how meteorologists inform you that even though it might be 5 degrees Celsius outside, it may feel like 15 degrees based on the wind chill factor. So when it's windy, it makes it even colder. Do that make sense?
Yeah.
Okay. In this photograph, this lady she probably feels cold because the wind blowing causes her body heat to leave her body and transfer into the cold air. Okay.
Yeah.
You understand that? So that could happen, especially when wind is actually present. Okay. So the faster the wind, the greater the convection. Does that make sense?
Yeah.
Okay. Someone said liquid. No. All right. Let's move on. Radiation. Real quick. Y'all know what this is? Have you seen one of these before? This is a heat lamp.
Oh.
You've seen a lot of these out of most restaurants and like outside, outdoors. You ever seen
Yeah.
that before?
Yeah.
You might,
They're always at downtown.
here downtown, you may have seen these on like patio heaters and backyard, stuff like that. Okay. They are tall in height, or they are really, really tall for a reason. They don't want you to actually bump into them and actually burn your head. Okay.
Yeah.
Most people know that the heat rises, so very little heat from the fire can come down to you via convection. All right. So most
Mhm.
of the heat transfer occurring here is through radiation. Meaning, if you stand in front of this or next to it, you'll feel the heat coming from it. Of course, is it wise for you to actually touch this?
No.
No, you should feel the heat
From the.
radiating or coming from this area to keep you warm.
Yeah.
Okay. Any questions about that? It says air from him is cold, so she can. This is delayed, really delayed. When it comes to insulation, insulation is a material that slows heat transfer. I know we are all familiar with oven mitts, okay? They
Yeah.
are used to protect our hands when we're going inside of the oven. Like this one here. Mine is kind of old, right? It's kind of old. But it's designed, this is a form of insulation. It slows heat transfer. So I can actually go in my oven, pull my little my grates out if it's hot, and it's not supposed to, it's designed to protect my hand. Okay.
Yeah.
So both of these are insulators right here. Okay.
That we're
Go
we're
ahead.
going over the lesson first, and then you're gonna have to answer the questions in the packet.
Well, this is actually week 3 packet.
Yeah.
We're week 3 packet. Okay. Same thing with our can of soda over here. Okay.
Mhm.
This prevents all of the coldness from leaving, or well, this prevents the hotness coming towards this can. You want to keep this as cold as possible.
Yeah.
Okay. All right. Let's move on to conductors really, really quickly. Conductors, can y'all see this?
Conductors.
Can you see this word? Hold on. Tap this up for you all. You see that now?
Mhm.
So conductors are materials that allow heat transfer. That allows heat energy to transfer. The cool thing about conductors is they're made of all different types of metals and irons and things of that nature. Okay.
Mhm.
Case in point, if we were to look into our own kitchens and take a look at some pots that we have, why are those conductors?
Because now that they're kind of like made with this kind of metal, heat can transfer so we can cook. It can transfer to the pot so we can cook something.
Right. So if I had my pan right here, y'all see my pan?
Yeah.
My pan has a metal handle on it. Okay.
Mm-hmm.
And of course, if I was to put it in on top of the stove, there's a great conductor because I am trying to actually cook my food. Okay. So the metal or the heat from the stove will touch the bottom of my pan. And then eventually, as it's cooking, you see I put my little potato in here.
Yeah.
I will boil my potato on here, and then that heat transfer will be, this pot is a great conductor of heat.
Yeah.
Okay. All right. Everybody understand that? Let me get a heart if you understand, please. Give me a heart. All right. Show me a heart if you understand. Okay. All right. So a quick little review. Excuse me. Quick review. We know a form of energy. Heat is a form of energy transferred by a difference in temperature. Heat flows from blank to blank. Give me those two answers, please, in the comment section. I need these two answers in the comment section. Heat flows from what to what?
Grace got it. Hot to cold.
Very good. Very good. Thank you. Thank you. Okay. Very good. From hot to cold. All right. We said conduction, transfer of heat between solids. Keep that in mind. It has to be solids. Okay. Convection, heat transfer from a liquid or a gas or fluid. Okay.
Yeah.
Radiation can transfer through empty space. All right.
Mm-hmm.
Any questions thus far?
If I were you, I would screenshot this.
Say that again.
If I was them, I would screenshot it for like just to take it down. I don't know, study it.
All right, so we can do that. Screenshot this if you will. Screenshot this if you will. All right, so I wanted to give you all some practical uses when it comes to heat transfer. We're about to do a video simulation so you can see how this works in your own kitchen. Okay? So please pay very close attention and chime in if you have any questions. Wake up, Momo.
I'm trying to.
We're almost done.
All right.
All right, so the big question here is what makes things hot or cold? How do things get warmer or cooler? We have already explored these items. Can y'all see this? Was this really clear?
I mean, I can see it.
All right. Oh my goodness. Trying to get it right on my screen, y'all. Hold on. Excuse me. Here we go. All right. So we take a look here. We have our thermal energy and our particles are moving at a moderate pace.
Mm-hmm.
Y'all see that? However, if I was to decrease the temperature, what can you predict will happen to these particles?
It will move like slower.
Absolutely, it's going to move slower. So let's Take a look here, make it colder, and move slower. On the flip side to that, the energy that's in the house. On the flip side to that, if I was to increase the temperature, what's going to happen to the kinetic energy?
It's gonna move faster.
It's going to move faster. It's going to increase. Okay? Now, let's take a look at this one. Now, this is what I wanted to show you all. Right here, we have a pot on an actual stove.
Mm-hmm.
Okay. Slow down and get pat. Yes, it'll move slower. It's less space. So right now we have a pot on the stove. Just this part right here, by touching the flame, the bottom of this pot is going to get hot. Correct?
Mm-hmm.
What type of heat transfer is that?
Conduction.
It's conduction. This is going to get hot. Whatever's inside is going to get hot and cook. All right, let's pay attention to what's getting ready to happen.
Mm-hmm.
Place a metal pot on a hot stove. The particles at the bottom of the pot are the first to gain thermal energy and increase their motion. The increased vibration of these particles transfers energy to other nearby particles as if they were connected on a spring. And these in turn move faster. Gradually, the whole pot gets hotter.
Absolutely. Eventually, the whole pot gets hotter. First, you have to start from the bottom, and then it went to the actual top. You understand that concept?
Mm-hmm.
Okay. It says heat from the fire is heating up the pan. Absolutely. All right. Take a look at this one.
When the water in the bottom of the pot is heated, its particles gain. Even though it's no longer over a stove burner, the hot pot gives off thermal energy through radiation. When this radiation strikes the material in the nearby thermometer, the particles in the material gain energy and move faster, so the temperature reading of the thermometer rises.
What happened there?
Radiation.
What about it? I think I skipped one. That's what I did. What about radiation? So
Light.
first, let me back up first. First, we let it boil.
Mm-hmm.
Okay. Then I was supposed to play this one. This was convection. You need to pay attention to how the particles are actually moving.
When the water in the bottom of the pot is heated, its particles gain energy and move faster. The heated areas expand and become less dense, and then rise through the cooler surrounding water in the process of natural convection. As the warmer water rises, the cooler, more densely packed particles move downward.
Okay, so you see how this cycle happens?
Mm-hmm.
Why does this become colder in a sense, or cooler in a sense? It was touching the flame here, but once it started to rise and travel and go in a cycle, what happens to it? It becomes what?
Colder.
Colder. Okay, so hot air does what?
Cold. Hot
Hot air rises
rises.
and cold air
Decreases.
sinks.
Sinks.
Okay, so think about this. It says the particles separated, the temperature rose. The cold air mixed with the hot air, but the hot air takes over. So what happens is once it's leaving the flame, once it's leaving the heat source, it tends to get cold. Do that make sense?
Mm-hmm.
However, once it revisits the heat source, it gets hot and the process go over and over again. Okay? I think I asked this question the other day. If I was to say if it was 90 degrees outside, what is the coolest place in your house?
The basement.
The basement. Because cool air sinks, very good, and hot air rises. Very good. All right. So we can move on to the very last one, which would be what? Radiation.
Mm-hmm.
Okay.
Even though it's no longer over a stove burner, the hot pot gives gives off thermal energy through radiation. When this radiation strikes the material in the nearby thermometer, the particles in the material gain energy and move faster, so the temperature reading of the thermometer rises.
Why is this temperature reading going up? If you notice from the beginning, it was all the way over here. But once this was in the air, the atmosphere, why did this temperature go up?
Because it's mostly because of the heat waves. Like the heat waves hit the temperature in the air, and that made it rise.
Absolutely. So it felt radiation. So when it comes to radiation, you don't necessarily have to be exactly like right next to something or touching it. That radiation, that smoke, that steam, it should reach you. You should be able to feel the heat coming from it. Case in point, who in here, how many of you all iron your clothes? Do you
Me,
iron your clothes?
me,
And you put water in the iron, correct?
yeah,
And it starts to steam up.
yeah,
How do you know when it's hot? Do you put your hands on it?
no.
What do you do?
You feel it.
You actually feel the radiation coming from the iron,
Yeah.
right? Okay, so that's another example. Okay. Are there any questions thus far? If you have any questions, please type them in the box, the comment section, please. All right. I wanted to give you all a physical science example. If you were at a campfire and it says, can you see that?
Now right there. Yeah, now I can.
So if you was in a campfire, picture yourself there. What do you notice? Why might you feel warmer? Why
Uh,
might you feel warmer at a campfire?
because the heat is like expanding in the air,
Okay, what else?
and then that's
So,
radiation.
so out of these conduction, convection, and radiation, what part will be considered conduction?
The marshmallows.
Right, because of what they're actually using their marshmallows, what they're using to toast their marshmallows. If you take a closer look, he has a wooden stick or a branch, and she has something made of metal. Now, why is the heat traveling up her metal rod?
Because it's made like it's the material for it to like heat up and stuff.
Thank you. So metal is a good conductor of heat. So would it be wise for us to use a metal rod when we're trying to toast marshmallows?
No.
No. All right. Very good. So that's why my man over here, is using the branch so he won't burn his hands. Okay.
Yeah.
And remember, conduction is direct touch. So if she leaves her hand on there long enough, we can can predict that she will burn her hands. Yes?
Mhm.
All right. Take a look at convection. What's happening here?
The heat is like flowing, like the gas is like flowing out the fire.
The gas is flowing up. Yep. So this portion right here is actually red, and this portion is blue. So it starts to do what as it goes further up?
It
As
gets
it leaves,
colder.
as it leaves the flame, what actually happens?
It gets colder.
Yes, it cools down. It gets colder. Very good. All right, let's go to radiation. What do those wiggly lines mean?
The heat waves.
Right, heat is radiating from the actual campfire. So someone could just be standing there. You know how you're kind of cold, you'll stand there and like try to
Yeah.
warm up. Just put your hands here. Okay. So heat is radiating. So a campfire is a good example that explains all three types of heat transfer. All right, so we're saying heat is rising up. Heat rises, it cools down. The heat is up, it gets colder. Yes, you all are doing a fantastic job with answering questions. Very good. Very good. I have one more thing to show you guys before we leave today.
What is that?
We're actually going to go over time today. Just bear with me. This is some food that remember we're going to use this as examples, Momo, but we
Oh
decided.
yeah. From my point of view, it looks like throw up.
Yeah, it probably does. All right. So here we go.
Simple terms, heat is the transfer of energy from objects of different temperature. As objects warm up or cool down, their kinetic energy changes. Kinetic energy is the energy of motion. Temperature is a measure of the average kinetic energy of the particles in an object. As temperature increases, the energy of motion increases. As the water warms up and the temperature increases, you can see an increase in the movement. Heat can be transferred in at least three ways: conduction, convection, and radiation. Conduction is a process in which the transfer of heat takes place between objects by direct contact. It is most often associated with solids. The key to conduction is direct contact. The heat of the pan is transferred to the many pieces. The energy of the frying pan is transferred to the eggs. Notice that they are in direct contact. Convection is heat transferred by the movement of a fluid such as air or water. When the heated fluid is caused to move away from the source of heat, carrying the energy with it, it occurs due to density. Lava lamps are examples of convection. As the liquid is heated, it rises and falls as it heats and cools.
You all have a question in your packet in regards to all of this, especially the lava lamp. There's a lava lamp question in your packet. Please be sure you all are paying attention.
Is that video on Canvas?
Yes.
All right, good.
As the paper burns, the air is heated up and begins to rise. The burning paper is swept up in the convection current, cools, and falls back down.
Why is that falling back down?
Because the heat is like leaving, and then once the heat leaves, it like cools down, and then it just fall
It
slowly.
sinks, right? So first it was hot, the heat went up. Once the heat left, it fell back down. Remember, hot air rises, cool air sinks.
These beams are another example of convection. As the beams warm up, they rise and then cool and fall back down.
Ooh.
So it gets cooler because, yes, absolutely, Grace.
Radiation is transmitted without any physical contact between objects. Watch how the temperature of the lamp is transferred to the thermometer without touching it. These alligators
Yes, Grace.
and lizards use radiation from the sun to warm their bodies. If you'd like to know more about heat transfer and conduction, convection, and radiation, this playlist will help.
All right. So hopefully that gave you all a better idea, or gave you some, basically finalize your questions you had with heat transfer to three types. What are they again,
Conduction,
Momo?
radiation, convection.
Conduction, radiation, and convection.
Convection.
Which one is direct contact?
Conduction.
Mm-hmm. So it's like the cycle we saw. Yes, it's in a cycle. Yes, the heat, it rose and then it actually sunk or fell once the heat was removed. Okay? All right, so this is what we're going to do now. Your exit ticket is up here, and it's also your exit ticket is here, and it's also on Canvas. If you want to take a screenshot, please do so. Take your screenshot. But this is also on Canvas. Give me a thumbs up if you've taken your screenshot. Give me a thumbs up if you've taken your screenshot. Okay. All right, remember, again, it's on Canvas, so you should be completing your exit tickets and warm-ups and anything else on Canvas. Well, Jewel, that's a very good point. Condensation has nothing to do with what we've been discussing. So you could basically eliminate a wrong answer choice. Condensation has to do with the water cycle. Okay? Milani, we're not done yet. All right. Here's the next steps right here. I want you all to take a look at this. Screenshot this. There's a Kahoot game that you need to play by Friday at noon. After you screenshot that, please give me a thumbs up. Okay. So hopefully everybody got what they needed today. I wanted to do a tour or some activities within the kitchen. However, I did not have enough supply. I didn't have any supplies actually. Hopefully you all will be able to do convection, radiation, and conduction in your own kitchens. So for an example, if you have potatoes, you can boil them on the stove and create mashed potatoes. Or if you want to make your own French fries, you can take potatoes and cut them up and put them in an air fryer if you all have an air fryer at your house. If you don't know what an air fryer is, excuse me, it uses air and gas, and it basically cooks the food using that without oil. If you take a look here, this is an air fryer. Let me turn it around so you can see. This is an example of an air fryer right here. Okay. So you can use that through convection. Of course, like I said, you can use a pots on a stove. All right. And you can also use your microwave. So if you want to make baked potatoes or something like that, you can also make it in the microwave. So you can make it in the microwave, you can make it in the oven. You can cut up your potatoes and make French fries, like I said, or you can make mashed potatoes. So that was the example I wanted to use today with you guys. If y'all have any questions, please email me or DM me, okay? Momo, you have any questions?
No, I understand everything.
Very good. Milani, you have any questions? Anybody else have any questions? Please pay attention to me. Who is Tokyo King? Who is that?
That's my best friend from Indiana. He needs to get off.
Yeah, I'm about to boot him out.
Bye, best friend. I hate when he do that. Always in my business.
All right. So again, hopefully, guys, everybody's good. Be safe. Do your classwork. If you have any questions, let me know. Talk to you later. Okay.
Bye, Miss Tate.
Bye bye. Love y'all.
Love y'all too.
Love y'all. Bye bye.